All right, we're continuing with the curve sketching series of videos. This is video number 5, and we're going to sketch this function. Okay, step 1, domain and range. What is the domain here? Well, the only domain issues are if we potentially divide by 0. That's it. It's not like we have a even root in the numerator or denominator where we can't have a negative number. We've got two polynomials, one in the numerator, one in the denominator. So the only issue here is dividing by 0. So when could x squared plus 1 potentially be equal to 0? Well, never. There's no x that you can input into x squared plus 1 and have this equal to 0. So the domain is all real numbers. Okay, now it's hard to see what the range will be, so let's continue with the rest of the analysis, and then we'll come back to the range. Okay, now x and y intercepts. X-intercepts, or y-intercepts, set x equal to 0 and solve for y. So you get minus 1 squared over 1. Okay, so 0, 1 is a y-intercept. Okay, x-intercepts, set y equal to 0 and solve for x. Okay, so this means when does x minus 1 squared equal 0? So when does x minus 1 equal 0? When x is equal to 1. Okay, so we're going to go from 3 to minus 3 on the y-axis, and then 10 to minus 10 on the x. Or no, I did that wrong. Okay, so x is equal to 1, y is equal to 0 is an x-intercept, and then x is equal to 0, y is equal to 1 is a y-intercept. Well, okay. This is 0.3, 0.6, 0.9, 1.2, so this is about 1. Okay, so there's the intercepts. Now let's check for symmetry. Is this function an even function? Okay, so y of minus x is equal to so x squared plus 1, and then you could write this as so minus 1, and then x plus 1 squared, and so this is x plus 1 squared over x squared plus 1. This is not equal to y of x. Okay, what about an odd function? So minus y of x is equal to what? Minus x minus 1 squared over x squared plus 1, and that's not equal to y of minus x. So it's not even or odd. What about periodicity? Is there some number p to where y of x plus p is equal to y of x? No. For like a rational expression like this, no. All right. Now let's check endpoint behavior. How do you check endpoint behavior? You come to the domain and take the limit as x approaches the endpoints. So what is the limit as x approaches negative infinity of y? Okay. So, okay, we've got x minus 1 squared divided by x squared plus 1. Okay, we want to store this. All right, there we go. So now let's take the limit as x approaches negative infinity of e. It's 1. Okay. Now the limit as x approaches positive infinity of the function is it's also 1. Okay, so we're going to have a horizontal asymptote at y is equal to 1. So there we go. There's y is equal to 1. Okay, next, let's get the critical points, both with respect to the first and the second derivative. Okay, so the first derivative we want to do is say, what is the derivative with respect to x? Okay, is there anywhere where this doesn't exist? No. Can't have any x that makes the denominator 0. So now let's solve for when this is equal to 0. X is equal to 1 or minus 1 or 1. Okay, so x is equal to minus 1 or x is equal to 1. All right, now let's evaluate these points. So minus 1, when x is equal to minus 1, what do we have? Minus 1 is minus 2. Minus 2 squared is 4. 4 over 2, so this is minus 1, 2. Okay, what about 1? 1 minus 1 squared is 0, so this is 1, 0. Okay, that's the first derivative. Now the second derivative. Okay. So now let's take the second derivative with respect to x of the equation. Okay, there's no points where this doesn't exist. Solve for when this is equal to 0 for x minus root 3, 0, root 3. Okay? Plus or minus root 3, and x is equal to 0. All right, so now let's get the equation e with x is equal to, let's start with 0, is 1. So 0, 1. All right, now we've got root 3 and minus root 3. So So 2 minus root 3 over 2. And then minus root 3, 2 plus root 3 divided by 2. Okay, now let's plot these points. All right, minus 1, comma 2, 0.3, 0.6, 0.9, 1.2, 1.5, 1.8, 2.1, so about right there. All right, 1 comma 0 is here. 0 comma 1 is here, so now root 3. And then, okay, let's see. First of all, root 3 is what? Root 3 is that. And then, what is this? So 1.73 and then 0.13. So 1, 2, that's about 1.73 and then 0.13. You go 0.3, so this is something like this. Okay, and then, so now minus root 3, and then whatever this is, 1.87 minus root 3. It's about right there. And then 1.87, 0.3, 0.6, 0.9, 1.2, 1.5, 1.8. About right there. Interesting. Okay. Okay. Now, if we didn't know this function at all, if we were just working this blind, the idea is once we have these critical points, we would take the limit as x approaches each of the points from the left and the right and see, does any of those limits go to infinity? If they do, it's a vertical asymptote. But we're not going to do that. We know we don't have vertical asymptotes here. If we're not dividing by 0 for a rational function, if there's no dividing by 0, it's not going to be a vertical asymptote. But in general, if you just think about it, if you're going to be analyzing a function like completely blind and you want to fully analyze it, that you would get the critical points with respect to the first and the second derivative, and then take limits as the function approaches, as x approaches each of those critical points from the left and the right of the function. But we don't need to do that here. Okay. So now let's get the intervals where the function is increasing and decreasing. So that has to do with the first derivative, and so the first derivative can only change from positive to negative or negative to positive at a first derivative critical point. So only at 1 or minus 1. Can the first derivative change signs? So let's get the derivative with respect to x. There it is. Okay. Now evaluate this with x equal to minus 2. It's positive, so it's increasing in this region. All right, now let's do, when x is equal to 0, it's also positive. We know because we can see that here. So it's increasing in this interval. What about when x is equal to something greater than 1? Well, we can see it's positive as well. Root 3 is greater than 1, and we know this is positive. Well, wait, no, what am I talking about? I'm sorry, no. This is evaluating the function. We need to evaluate the derivative. So, yeah, okay, we need to evaluate the derivative at x is equal to 0. That's negative. Okay, so it's decreasing here, and then evaluating the derivative at something greater than 1, so 2, it's positive. So increasing. Okay. All right, intervals of concavity. Okay, so what are the critical points with respect to the second derivative? You've got positive root 3 and negative root 3. There are your intervals where the second derivative can change signs. Okay, so let's take the second derivative. Okay, now evaluate this. With x is equal to something less than minus root 3, so minus 2. It's positive, so concave up. All right, now something between minus root 3 and 0 would be minus 1. It's negative there. Okay, now change this to 1. Okay, so now it's positive, and then let's go positive 2. Negative. Okay. All right. Okay, this curve is continuous everywhere, and so we just need to look to see what the local maxes and mins are. We just come to the critical points with respect to the first derivative and see is there a sign change? If the sign of the first derivative changes at the critical point, then it's a local max or min. Here we go from increasing to decreasing. This is a local max. Here we go from decreasing to increasing. This is a local min. Okay, inflection points it has to be at a point of continuity. The function is continuous everywhere. So does the second derivative change signs across a point, a critical point with respect to the second derivative? If it does, it's an inflection point. It does at each one of these points. So they have 3 inflection points. Okay, so the local max and min here, right? That's where the slope is going to be 0. So we're going to have this 0 slope here. And then, or no, this is here, 0 slope. Okay. Okay, what about this? 0, 1. Is that an inflection point? Yes, it is an inflection point. So we're going to be, you can see we're going to have to be concave down to get to this point, and then we're going to switch to concave up to get to this point. And that's why this is an inflection point. So like that. And then we have to switch to concave up here. And then it's also a point of 0 slope. So it's an inflection point, and it's a point of 0 slope, and it's a local min. You see? Same thing here. This is well, no, it's not an inflection point. We didn't switch to concave down. Never mind. We didn't switch to, yeah. So this is just a local min. We didn't switch concavity. We switch concavity at this point. Right? We're concave up, then we're going to switch to concave down. Inflection point. Like that, okay? So if we analyze this, we should be increasing all the way from negative infinity to x is equal to minus 1. Yes. And then from minus 1 to 1, we're decreasing. And then from 1 to infinity, we're increasing. From negative infinity to this minus root 3, we're concave up. And then from minus root 3 to 0, we're concave down. And then from 0 to root 3, we're concave up. And then from root 3 to infinity, we're concave down. All right. The y-intercept is at 0, 1. The x-intercept is 1x-intercept. Let's check that. 1x-intercept, or no, yeah, 1x-intercept at x is equal to 1. The endpoint behavior is correct. As the x approaches plus or minus infinity, the function is approaching 1. Y is equal to 1. And so there you go. That's the graph.